Okay, so now we're officially moving on to calculus with polar. And the very first thing that we're going to do is we're going to talk about dy dx, because remember with calculus and polar, it was dy dx and then dr d theta and then area. We're not going to get to area today, probably. On your homework tonight, there's nothing about area within polar. But what is there is dy dx and then dr d theta. So let's start with dy dx, because dy dx is easy to understand because we've dealt with it before. Dy dx is simply the slope of the tangent line. So for something that's polar, right, it could look something like this. Let's say that we have our axes here, and the polar curve might do something like this. Right? And so it might continue this and like get a little bit further and further away from the pole, but have a similar type of shape. So for something like this, if I were to choose at any point on this polar curve, like right here, if I'm asking you what is dy dx there, what can you definitely tell me about dy dx at that point right there? It's what? Negative, correct, because the slope of the tangent line right there falls from left to right. So I know that dy dx is less than 0, for sure there, right? And then right here, a horizontal tangent, we would have that dy dx is equal to 0 there, okay? So now we need a way to represent dy dx if something is given to us in r's and thetas. Okay, so here we go. We start with dy dx, but then we say, well, hold on a second, isn't this the same as d theta of y over d theta of x? So this is the same as dy d theta over dx d theta. The same reason that in parametric we had dy dt over dx dt was equal to dy dx, correct? So now we're just saying dy d theta over dx d theta is equal to dy dx. So that shouldn't be a surprise. And now we talk about a different way to represent y using r's and thetas. Is there a way that we have used, or that we can replace y with r's and thetas? Yeah, so this is just d theta of, what is y? R sine theta divided by d theta of r cosine theta, because r cosine theta is what x is equal to. So now I'm going to pick up on the board so it's easier to follow. So we have that dy dx is equal to d theta of r sine theta over d theta of r cosine theta. Now this is r times sine theta and r times cosine theta, so there's a product there of r and sine theta and then r and cosine theta, so I need to use the product rule. And with it, the variables aren't always what I'm taking the derivative with respect to, right? So r, I need to deal with that using implicit differentiation. So let's do the derivative of only the numerator. So what's the derivative of r times sine theta with respect to theta? So it's going to be the first, which is r, times the derivative of the second, which is cosine theta, plus the second, which is just sine theta, times the derivative of the first. What's the derivative of r with respect to theta? Just dr d theta. Now let's look at the denominator. It's going to be first times the derivative of the second, which is negative sine theta, plus the second times the derivative of the first, which again is just dr d theta. So this is going to be my big important note that I'm going to say. So dy dx is equal to dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. So I'm just rearranging that numerator and that denominator to have the dr d thetas come first. So it's just dr d theta times sine theta plus r times cosine theta divided by dr d theta cosine theta minus r times sine theta. And this is dy dx. This is the formula that you just need to know. But what if I kind of forget if it's plus or minus, whatever? You can always derive it the same way that we just did, knowing that dy dx is just the same as dd theta of y over dd theta of x, and then replacing y and x with what they're equal to in terms of r's and sines and cosines of thetas. Yes? Okay. So now let's go through an example. So I copied the note that he had, and then here's the first example that he has. So here we go. It says, find an equation of the line tangent to the polar curve r equals sine 2 theta when theta equals 3 pi over 4. Okay, so now it's not only the slope of the line, but let's start with that. Let's first find, let's find the slope. So dy dx evaluated when theta equals 3 pi over 4. That's what I'm looking for. Agreed? So this is equal to, okay, and again, we have that r is equal to sine of 2 theta. So if r is equal to sine of 2 theta, what is dr d theta? That's correct. Say it louder. So we get 2 cosine 2 theta. Does everybody see that? Because if r equals sine of 2 theta, I'm taking the derivative with respect to theta of each of those. This gives me dr d theta on that side, and over here it's the just taking the derivative of sine of 2 theta with respect to theta is just differentiate normally, explicitly, which is cosine 2 theta times 2. Sine of 2 theta, the derivative is cosine of 2 theta times 2. Correct. So where the dr d theta is, I'm saying dr d theta is just equal to that. Up there. So then that's times sine of theta. Do you see that? Right there, sine theta. Plus r, well what is r? Sine of 2 theta. Times cosine theta. Divided by dr d theta, I've already found that, that's my 2 cosine 2 theta, times cosine theta, minus r, well that's still sine of 2 theta, times sine theta. So now it's this guy evaluated at theta equals 3 pi over 4. Okay, so now we plug in 3 pi over 4 every place that there's a theta. So this is equal to 2 times cosine of 3 pi over 2. Do you see why it's 3 pi over 2 right there? Because it's twice what 3 pi over 4 is. Twice 3 pi over 4 is 6 pi over 4, also known as 3 pi over 2. Times sine of 3 pi over 4 plus sine of 3 pi over 2 times cosine of 3 pi over 4 divided by, so really quickly I've only plugged in that theta value every place there's a theta in my numerator, and I got this. Does everybody see where that's coming from? So now let me plug it in for every theta value in the denominator. So this is going to be 2 times cosine of 3 pi over 2 still, times cosine of 3 pi over 4, minus sine of 3 pi over 2 times sine of 3 pi over 4. So this is equal to, so what's cosine of 3 pi over 2? 0. So that makes this, so if that's 0 and that's 0, this whole thing is going to go away and that whole thing is going to go away. Do you all see that? Yeah? So then in my numerator, now all that I'm going to have is sine of 3 pi over 2, so what's that? Negative 1 times cosine of 3 pi over 4. 3 pi over 4 is located in the second quadrant, so it's going to have a negative x value and a negative y value, so it's going to be negative root 2 over 2. So negative 1 times negative root 2 over 2 is root 2 over 2 divided by, so here we go again, so that's negative 1 times, that is just 1 times sine of 3 pi over 4. So it's negative root 2 over 2. So this is equal to negative 1. That's the slope of the tangent line for this polar curve at x equals 3 pi over 4. Why is negative 1? Because anything over its negative self is negative 1.
Wait, for how do you get a negative 2 over 2? Since sine of 3 pi over 4 is just
Negative 1 times this negative
positive.
is a positive 1. Sine of 3 pi over 4 is negative root 2 over 2.
But in the second quadrant, the y is positive.
Sorry, you're right. Thank you. The x is negative, the y is positive. Silly Mr. Groller. Yes. In my head, I even said it. I said it's negative and negative. But then in the second quadrant, I'm thinking negative, but it's positive. The y value is positive, correct? So therefore, it's going to be positive. So that is the slope of the tangent line there. So now let's use that and finish this, because what they are asking is for the equation of a line. So it's going to be y minus something equals 1 times x minus something. So what is the y value? So what's the y value? Well, y is equal to what? R sine theta, right? So at theta equals 3 pi over 4, y is equal to r. So this is my r. R at 3 pi over 4 is equal to sine of 3 pi over 2, which is equal to what?